Aging does not begin in your wrinkles, your joints, or your memory. It begins much deeper, inside microscopic structures that most people never think about. Aging begins in the mitochondria. These tiny organelles live inside almost every cell of your body, and their primary job is to produce energy. Every heartbeat, every thought, every muscle contraction, and every repair process depends on mitochondrial function. When mitochondria are strong, cells thrive. When mitochondria weaken, aging accelerates. Mitochondria are often called the power plants of the cell, but they are far more than simple energy generators. They regulate metabolism, control cellular stress responses, influence inflammation, and even decide when a cell should repair itself or die. Because of this central role, mitochondrial health determines how well cells function over time. Modern biology increasingly recognizes that mitochondrial decline is not a side effect of aging. It is one of its earliest and most important drivers. In youth, mitochondria are highly efficient. They convert nutrients into energy with minimal waste and minimal damage. As time passes, this efficiency slowly declines. Mitochondria begin to leak energy and produce more reactive oxygen species, unstable molecules that damage proteins, lipids, and DNA. This damage feeds back into the mitochondria themselves, impairing their function further. Aging becomes a self-reinforcing cycle that starts at the cellular power source. One of the most critical aspects of mitochondrial aging is that mitochondria have their own DNA. Unlike nuclear DNA, mitochondrial DNA lacks robust protective mechanisms and is more vulnerable to damage. Over time, mutations accumulate within mitochondrial DNA, impairing energy production. These mutations are copied each time mitochondria replicate, gradually spreading dysfunctional mitochondria throughout tissues. This process is strongly associated with declining muscle strength, reduced brain energy metabolism, and increased vulnerability to age-related disease. Cells attempt to manage this damage through quality control systems that remove defective mitochondria and replace them with healthy ones. In youth, this system works efficiently. With age, mitochondrial quality control becomes less effective. Damaged mitochondria persist longer, producing less energy and more harmful byproducts. This shift does not cause immediate symptoms, but it gradually reduces cellular resilience across the body. The consequences of mitochondrial decline appear first in high-energy organs. The brain, heart, muscles, and liver are particularly sensitive to energy shortages. Early signs are subtle: slower recovery after exertion, reduced mental clarity under stress, diminished endurance. These changes are often dismissed as lifestyle issues or temporary fatigue, but they reflect a deeper biological shift in cellular energy capacity. Mitochondrial dysfunction also plays a central role in inflammation. As damaged mitochondria accumulate, they release signals that activate immune pathways. This contributes to chronic low-grade inflammation, a hallmark of aging. Inflammation further damages mitochondria, creating a vicious cycle in which energy decline and inflammation accelerate one another. This cycle has been observed consistently in aging research across multiple tissues and species. Another critical link between mitochondria and aging lies in cellular communication. Healthy mitochondria send signals that promote repair, adaptation, and survival. Dysfunctional mitochondria send distress signals that shift cells toward defensive, inflammatory, and degenerative states. Over time, tissues dominated by stressed mitochondria lose their ability to regenerate effectively, leading to gradual functional decline. Importantly, mitochondrial aging does not happen all at once. It begins early, progresses slowly, and accelerates when repair mechanisms can no longer keep pace. Lifestyle factors such as chronic stress, poor sleep, nutrient imbalance, and physical inactivity place additional strain on mitochondria, increasing damage and reducing renewal. Conversely, conditions that support mitochondrial turnover and efficiency are consistently associated with slower biological aging. What makes mitochondrial aging particularly deceptive is that it occurs while cells continue to function. The body compensates remarkably well, masking energy deficits for years. By the time mitochondrial failure becomes obvious, Much of the damage has already accumulated. This is why aging feels sudden, even though it is anything but. At its core, aging is an energy problem. Cells lose the ability to generate sufficient energy to maintain structure, repair damage, and adapt to stress. Mitochondria sit at the center of this process. When they falter, everything downstream begins to fail more quickly. Aging does not start when you feel old. It starts when your mitochondria lose their youthful efficiency. Long before symptoms appear, long before decline is visible, the cellular engines that power life begin to slow. Understanding this shifts how aging is viewed, not as a surface-level change, but as a deep biological process rooted in the cell's ability to produce and manage energy.